This is the lecture for the concentration and dilution section of Unit 8. In this lesson, we're going to explore what exactly is solution concentration, what's the difference between dilute and concentrated, what is molarity, and then we'll also look at some dilution problems. In the simplest terms, concentration is just a comparison of the amount of dissolved solute compared to the amount of solvent. I'll give you an example you may have some experience with. Let's say that your neighborhood's going to have some garage sales and you decide that you want to have a Kool-Aid stand, all right? So let's say for whatever reason you get this idea, hey, I can really stretch my dollar and make this Kool-Aid go really far. You know, instead of making just a pitcher of Kool-Aid, let's say you get like one of those 5-gallon, igloo coolers, with the little spout on it, and you're like, well, I'm going to fill this thing full of water, and I'm just going to put 1 packet of Kool-Aid in there and a couple of cups of sugar and stir that up and sell it for 25 cents a glass. Now, while, technically it's Kool-Aid, it's not water, it'll have some color to it. Well, the thing is, it's going to be really weak, really dilute. All right, it's not going to have a lot of flavor to it. And so that would be when you have a lot of solvent, but not a lot of dissolved solute, that is a dilute solution. Conversely, let's say, the next year you feel kind of bad about cheating all those customers out of their hard-earned quarters. And so you decide you're going to make it up to them. And so instead of getting that entire big cooler of Kool-Aid, and you're not even going to make it in a pitcher, you're going to make it in the individual cups. And so you're going to take a cup and fill it with some water, and right in the cup you're going to put that full packet of Kool-Aid and full cup of sugar in there and serve that. Give them some really intense flavor. That would be the exact opposite of dilute. That would be concentrated, okay, which means you have a lot of dissolved solute per the amount of solvent. So dilute means, there's not a lot, but concentrated means there's a lot of stuff dissolved in there. As chemists, we need a way to measure the concentration. The most common unit, the one that we're going to use, is one called molarity. Notice molarity is abbreviated with a capital M. And so anyway, molarity is a unit of concentration. You may have seen some things written, like this. So 6.0 M hydrochloric acid or 1.0 M hydrochloric acid. What that's telling me is the concentration, how much hydrochloric acid compared to the amount of water. This solution is a lot more concentrated than this one. This is the formula for concentration or for molarity. So molarity is just the moles of solute divided by the total liters of solution. So molarity is essentially moles per liter. Molarity problems are kind of easy because, it's just a simple division. And as long as you know the moles and you know the volume, you can solve for molarity. So in this example, let's take a look. It says, what is the molarity of a solution that's composed of 5.85 grams of potassium iodide dissolved in enough water to make 0.125 liters of solution? So first thing, we need to know our formula. Molarity is moles over liters. Okay. Well, first thing you should notice, okay, we're trying to solve for molarity, so we don't know molarity. I look for moles. I don't know moles yet, but notice I know grams. And this is old hat. You guys know how to do this. We've been doing this kind of calculation for a long time. I can convert the 5.85 grams of potassium iodide into moles by using its molar mass. And so I'm just going to set up my calculation like we've done in the past. 5.85 grams of potassium iodide. Well, I want to put the moles on top, and I want to put 1 mole. Right? Whenever it's moles and grams, it's always 1 mole. And then I look up the individual masses, so it looks like potassium's 39.10, iodine is 126.90. So if I add those up, the mass is 160 grams of potassium iodide. Grams of potassium iodide cancel, and so if I divide 5.85 by 166, I get 0.0352 moles of potassium iodide. Well, now we know the moles. That's great. And now, if I just take those moles and divide them by the liters, 0.125 liters, well, I have moles over liters. That is molarity. So I punch that into my calculator, 0.0352 divided by 0.125. And with sig figs, my answer should be 0.282 capital M molar potassium iodide. And it's just that easy. Okay, here's another example. I want to know what the molarity is of a solution that has 0.09 moles of sodium sulfate, and it looks like it's dissolved in 12 milliliters of solution. So this is one thing you need to be aware of. A lot of people will sometimes kind of overlook that. The thing about molarity, it has to be in liters. So if you have any other unit of volume, you must convert it into liters. So this isn't really as straightforward as it looks. In looking at this, so once again, molarity is moles over liters. Fortunately, we know moles this time, so I'm going to go ahead and just put the 0.09 moles of sodium sulfate. Okay, the thing I don't know is the liters, but I do know the milliliters. And so we have to go back to our metric system or SI system conversions, right? And you have to recall, what does that prefix milli mean? Well, milli means 1/1000th. And so that essentially means there are 1,000 milliliters in 1 liter. I want to put the mils on bottom and the liters on top. And as you recall, I always give the bigger unit the value of 1. So 1 liter is 1,000 mils. Mils cancel. If I take 12 and divide it by 1,000, I end up with 0.012 liters. And so I'm going to just plug this into my formula. I now have moles over liters. If I do this and divide, I get 7.5. And then I have to round that up to 8 because of sig figs. There's only one sig fig in 0.9. So this would be an 8 molar sodium sulfate solution. Okay, this is just another way of looking at a concentration or a molarity problem. This time, notice it gives us the molar concentration and the volume, but I need to know, if I wanted to make this solution, how much sodium hydroxide I would need to weigh out. And so once again, let's look at our formula. Molarity is moles over liters. Well, this time I'm given the molarity. So I'm going to go ahead and just plug that in, 0.30 molar. I do not know the moles or the mass, so I'm going to put my X there because that's the unknown. The volume, I don't know the volume in liters, but I know it in mils, so I can convert those mils to liters just as we've done before. 25 milliliters, well, 1 liter, there are 1,000 mils. Mils cancel if you take 25 divided by 1,000. 0.025 liters. So I'm going to plug that in. So essentially what we need to do now is we need to get X by itself. And so, how do I do that? Well, I cross multiply. So essentially what's going to happen is that this 0.025 liters has to come up here. And so I end up with this. 0.30 molar, which is really moles over liters, right? And if I multiply this by 0.025 liters equals X, well, I have liters over liters. That's going to leave me with moles. So if I take 0.3 times 0.025, that's going to tell me that I have 0.0075 moles of sodium hydroxide. But notice, I want to make this, so I need to weigh this stuff out on a balance. And unfortunately, there isn't anything such as a mole balance. They don't exist. I have to measure in grams. And so now I just have to use dimensional analysis and molar mass to convert those moles into grams. And so I'm going to start with a 0.0075 moles of NaOH. I'm kind of running out of room here. And so the moles need to go on bottom, so they cancel. I'm going to put 1 mole of NaOH and its molar mass. If I add up sodium and oxygen and hydrogen, that ends up being 40 grams. And so if I take 0.0075 times 40, you get, with sig figs, 0.30 grams of NaOH needs to be weighed out and diluted. You may be sitting there and asking yourself, why do I care about concentration, dilution, all this business? I'm never going to use this in my real life. Well, the thing you need to recognize is that there are applications that really most people are going to need to be aware of as you travel through this world. One of the things you're going to notice, this is Prestone, this is antifreeze. You can go buy this stuff. I think these are prices I obtained from Walmart's website. Notice this is the same stuff. So we have Prestone, Dex Cool, same stuff. Let's say you see these 2 jugs, they'd be sitting next to each other on the shelf. Notice that it's sold in a gallon jug. This one costs $14.27. This one's only $12.47. You're like, oh man, this is a way better deal. It's a couple bucks cheaper. And not only that, but it advertises, you can't really see it, but this stuff is pre-mixed. And so essentially what that means, it's 50-50. Regular antifreeze, you can't just dump that into the radiator of your car. Essentially what antifreeze is, it's ethylene glycol. And what it does, it just has a really low freezing point. And so you can put that in your car's engine, and what it does is if the temperature gets cold like it does in Nebraska, it prevents the radiator from freezing solid. And the thing is, though, is you can't use just pure antifreeze because why you have this stuff in your radiator, the coolant, is because what it's doing is taking heat from your car's engine and dissipating it through those real thin aluminum fins in your radiator and getting that heat out into the environment. If the heat stayed in your engine, it would cause your engine block to crack. And so they need a substance that's really good at transferring heat. Well, water is great at picking up heat and transferring it from one place to another. The only thing is that in the winter it solidifies. And so what you need to do is you need to add Prestone or antifreeze into your car's radiator. And so the optimum mixture happens to be 50-50. And so, people would be apt to go to the auto supply store, or go to Walmart, and you're like, oh, well, this is awesome. This stuff's already pre-mixed. I don't have to mess with diluting it down with water. I can just take the cap off and dump it in the radiator and be on my way. But what you need to be aware of, if you look at this, you kind of have to understand, this one's full of, the one over here on the left, this one's full of antifreeze, but this one's only half antifreeze. The rest of it's just water. And so if you look at it, essentially what you're doing, so this one's $14.27 for the entire contents, which it's all antifreeze. But this one is $12.47, and essentially what you're doing, if you want to look at it as far as like halvesies, how much the stuff's costing, well, let's say that the bottom half's antifreeze and you're paying half of that's what, $6.24? Well, guess what? The other half, you're paying another, I guess it'd be $6.23 would add up, but this is for a half gallon of water. That's pretty expensive water. Well, let's just pretend the water itself the cost of water is negligible. A half gallon of water costs nothing, right? It's not like they're filling it with bottled spring water. It's just tap water. So, if you want to look at just the price of this, essentially what you could do is you could take this $12.47, and let's just pretend that $12.47 is the total cost of just the half gallon of antifreeze. So, if you double that, what you have to realize is that you're actually paying, what, 24? Yeah. I don't know what's going on there. You're paying like $24.94 per gallon for the same stuff, the exact same Prestone. This one's just been diluted down. You'd be better off buying this one and just dumping half of it out and filling the rest with hose water. Don't dump it out though. Just put in some other container and save it. But way cheaper to buy it this way and add in some water. If you guys don't want to do it and you get old and you have to make this decision, call me. I'll come over and I'll dump half of that out for $10. All right. The way dilution problems work, it's actually they're pretty darn simple. Here's the best part about it. Here's the formula. You have an initial molarity and an initial volume. It is equal to the final molarity and the final volume. That's it. And this is the best part about it. You don't even have to convert the mils to liters like we did before, because what's going to end up happening, the units end up either canceling or it's just going to give you units in mils. So you don't have to change them. For the molarity problems you do, these you do not. So anyway, let's work out a couple. Okay, let's say I need to make a 50 ml solution of a 0.150 molar sodium hydroxide solution. I go back in the storeroom and I find I only have 0.25 molar, and I don't want to waste it. How could I dilute it down to get the concentration of the solution I need? All you have to do, guys, is plug in the values. And so if I look, the initial molarity, let's just call that 0.150 molar. Okay, and then I'm going to multiply that times the volume, which that's 50 mils. And let's see, I have the second molarity that was given was 0.250 molar. I ran out of room. I didn't plan very carefully. And then I'm just going to try to squeeze this in here. The unknown volume is X. Well, here's the deal, guys. You got to get X by itself. Fortunately, it's very easy. All you have to do is divide by 0.250 molar. This goes away. Molar goes away. I'm left with milliliters, which is a volume, so this is good. Okay, if I get out my magic box and I hit 0.150 times 50 divided by 0.250, what you're going to find out is going to spit out 30 is the answer. Now, what you have to understand is that you would take 30 mils of sodium hydroxide. Now, but what you have to understand is that that's not changing the concentration. If I pour out 30 mils of this stuff, it's still this concentrated amount. It's still the 0.250. Just because I take it from a big container and pour it into a smaller container, it didn't change the concentration. And so to make it, what you have to understand is that we're changing it to, we want 50 mils of this. Well, I poured the 30 mils out. That means we need to add 20 mils of water to it. And so that's really the only part you need to be aware of, is that a lot of times it's going to ask you, how to make a solution. So you need to put the other half in there. So, just dumping it in the smaller container doesn't change the concentration. You have to dilute it with water. Okay, here's just another example. Wants to know how many mils of a 2 molar magnesium sulfate solution must be diluted with water to prepare 100 mils of a 0.4 molar magnesium sulfate solution. So once again, it's really just the same thing. Formula M1V1 equals M2V2. And so let's just call the initial molar 2.00 M. And it doesn't even matter which one you call the 1 and 2, because it's an equality. It works out the same regardless. I don't know how many mils. I don't know the volume, so I'm going to call that my X. Let's see, my other molarity is 0.400 molar. And then my other volume is 100 mils. Well, all I have to do is solve for X. I need to get it by itself, so I'm going to divide by 2 molar. This goes away. Molar goes away. So if I take 0.4 times 100 divided by 2, in doing so, this is going to tell me that I need 20 milliliters of that magnesium sulfate solution. And notice, because I'm trying to get to 100 mils, that means I have to add to it 80 mils of water. That's what's going to dilute it down. So you have two parts. You have to tell me how much of the solution I need to pour out and how much water I need to dilute it with. Okay, last one, and you guys will get some practice. Let's say I want to prepare 100 mils of a 0.2 molar hydrochloric acid solution from a 3 molar stock solution. So once again, let's look at the formula. M1V1 equals M2V2. Let's see, initial molarity, 0.20 molar. And let's see, this is going to be 100 mils. And it looks like the other one is 3 molar, and I do not know the volume. Okay, so I need to rearrange and get X by itself. That means I'm going to divide this side by 3M, the 3 molar. Molar cancels. If I take 0.2 times 100 divided by 3, you get like 6.7, but because I only have one sig fig here, I've got to round that up to 7 mils of the hydrochloric acid. And then to make the 100 mils, I would need 93 mils of water. Fair enough? All right.